Okay, let's start this class. Yeah, we have already finished chapter 1 and chapter 2. The chapter 1, we talk about the signals and systems. Actually, it's a general chapter. We just talk about what is signals and what is systems and what the properties of a signal is, what signal are, and what properties does a system have? Yeah, so and chapter 2, we just focus on LIT system. Yeah, yeah, here. Yeah. Actually, yeah, I'm just talking about we have already finished the chapter 1 and chapter 2. Yeah, chapter 1 is about signals and system, and it's a general chapter for the signals and systems. We talk about what is signal and what is a system, and what the properties signal has, and what the properties system has. Yeah, this is for the chapter 1. And the chapter 2, we focus on a special system. What is that? Chapter 2. Huh? LTI, yeah, LTI systems. Yeah, for the LTI systems, and actually, why we want to focus as LTI system? Because in the real world, in the real applications, many systems can be modeled as a LIT system. Yeah, so and for the LIT system, we know like the output can be represented as what? Input signals convolution with impulse response. Yeah, and then for the DT LIT system and the CT LIT system, we can use the convolution sum and convolution integral to represent the whole system. Am I right? Yeah, so that's the reason why we want to focus on LIT system, because it's easy for us to represent, to get like that. And for the chapter 3, we began to talk about Fourier series. Have you ever heard this before? What's that? You know? Okay. Yeah, don't worry. After this chapter, you will know what is Fourier series. Okay. Before we talk about this, a Fourier series, let's talk about what are we in the big pictures. Do you know, do you remember when we talk about in the class 1, in the beginning of this class, we talk about in this course, we involve 5 different questions. The first one is how to represent a signal, am I right? And then how to acquire a signal. And the third one is how to analyze a signal. And and then how to process a signal and how to transmit a signal. Yeah, actually, for the chapter 1 and chapter 2, which one do you think we have already talked about? Yeah, that's right. For the chapter 1 and chapter 2, we try to present a signal like the convolution sum, convolution integral, am I right? Try to use some properties to simplify that, am I right? Yeah, but this chapter, we will try to analyze the signal. Yeah, the Fourier series, actually it is a tool help us to analyze the signal. Okay, yeah, let's talk about this goal. Yeah, firstly, we will introduce harmonically related complex exponential signals. This one, actually, this is special signals. And we will talk about why we want to talk about this one. And then we will try to introduce harmonically related sinusoidal signals, this one. And then we will try to represent periodic CT signals via harmonically related complex exponentials or sinusoidals, which has another name, Fourier series representation. Actually, for the exponential complex exponential signals and the sinusoidal signals, we have already talked about those 2 signals before. I'm right. Yeah, you know that. Do you remember? Yeah, the sinusoidal signal and the Do you know why we always talk about those two signals? Do you remember? Actually, there is a very important statement. Do you remember? We know. Actually, there is a person called Fourier. He after some experiments and after some labs, he found any periodic signals can be represented as a sum of sinusoidal signals. Do you remember? Yeah. Actually, the complex exponential signals, it is sinusoidal signals. It can be transferred to the sinusoidal signals. Why? Because based on an equation. Do you know what is equation? Yeah, Euler equation. The Euler equation can transfer the complex exponential signal to the sinusoidal signals. Since any periodic signals can be represented to sinusoidal signals, so which means any periodic signals can be represented as a complex exponential signals. Yeah, because those are same thing. It can be transferred. Am I right? Yeah, so that's the reason why we want to focus on the complex exponential signals as a sinusoidal signal because it is kind of any periodic signal. Am I right? Yeah. Then let's talk about one very important thing. Actually, we talked about these things before. Time domain. Like what is time domain? Yeah, something related to time. Am I right? The time is what we focus on. Yeah, this is a process, preparation process. Yeah, if we want to cook this soup, and we start from 8 p.m. and 4 different items we need. The first one is sugar and red bean and tomato and water. And at the beginning of preparing this soup, we add 1 sugar, 3 red bean, 4 tomato. This is just a portion. At 1 water and 1 portion water. And at 6:01, and we just add 1 sugar. And you can see we just add different things in the specific time. All right. This is the soup preparation process, which means we just follow this recipe, like it's kind of recipe, right? We follow this recipe, put different things in different time in the time domain. Am I right? We can cook this soup after maybe 1 hour. If we need 1 hour to prepare this soup, which means after one hour we can get this soup. Am I right? Yeah, this is time domain. Okay, let's talk about the other one. Frequency domain. Actually, frequency, what is frequency mean? How frequency happen? Yeah, how frequency happen? Yeah, you can see if you observe, like this is time domain, right? But for the frequency, which means like you can see every 1 second you put 1 sugar. You notice that? Every 2 seconds you put 3 red bean. And every 3 seconds, you put 4 portion tomato. And every 4 seconds, you put 1 portion water. All right? So for the frequency domain, which means every 1 minute put 1, this is frequency domain. Like, which means if we want to represent one thing, or 1 item, 1 thing, we can represent these things in different domain. Am I right? In time domain and in frequency domain. Those two representation also like always works. Like all works. All works, am I right? That makes sense to you. Yeah, if I give you this time domain like recipe, you can cook this soup, am I right? If I give you this frequency domain like recipe, like I let you start from 6. Every 1 minute you put 1, I give you this after one, just give you after 1 hour you will the soup will be ready. So you can also get this soup ready, am I right? Yeah. So this is just the difference between time domain and frequency domain. Okay, let me ask you a question. like does anything, any event can be represented in time domain and frequency domain? Like does any event or things can do, yeah, you can do all the events or things be represented by time domain and frequency domain at the same time, like both. Yeah, can all things or events can be represented in time domain and in frequency domain? Yeah, that's right. You can see you can represent everything, every system in frequency domain, also in time domain. Yeah, that's the reason we want to learn both. Okay, let's try to see the time domain again. You can see this if we draw use the figure to represent how to make this soup. And at the beginning, at the 8 p.m., we just put a different item, right? Like in different portion. And at in like 6 1, we just put sugar. And if in like I think I need to, yeah, the color is not very obvious, but you can understand. It's just like in time domain, we just in different time, we put different things, am I right? So this is just the soup, like it's, and in frequency domain, you can see. I just give you this. This is just like the frequency, am I right? Yeah, like in 1 second, in 2 seconds, in 3 seconds, every 3 seconds, every 4 seconds, I put a different portion, am I right? This is you represent the event in frequency domain. Yeah. So let's compare. Yeah, you can see this is the time domain to represent how to make a soup. This is the frequency domain how to make the soup. You can see for the time domain, it should be like until the soup is ready. Right? For example, it's 1 hour. So did you find out the difference? Why we want to represent things in frequency domain? Since the time domain, yeah, it's very obvious, it's very direct. Why we want to represent things and events in frequency domain? You're saying why we want to do that? Yeah. Why we want to use representative in frequency domain? Since
maybe like one reading to one.
Yeah. One is what?
More like specific on like the time.
Yeah.
And stuff, and that was just telling you like how much sugar you need, how much sugar you need. That's telling you that you need to actually do everything.
Yeah, that's right. Yeah, this is your observation. Yeah, but why we want to because you can see for the time domain, it's very easy for us to understand, am I right? If I give you this time domain like a recipe at 6 p.m., if you start from 6 p.m. and you just put this thing at 601, you put this one, at 602, you put this one, am I right? It's very obvious, direct to you, am I right? It's very easy to operate. But why? If I give it this to you, can you get this soup ready? No? Are you sure?
No.
No, you cannot get this soup ready if I give you this one. Why?
It's really how many.
Yeah, I will tell you. Like you can start from 6 p.m. Yeah, if I let you start 6 p.m. Since our class start from 12. Yeah, like I will at the beginning of this class, and I will let you to get this soup ready and start from 12 o'clock. I give you this thing. Can you get this soup ready after this class? Huh? Why? What? It's not that easy. Forever now? Yeah, I give you if I give you this one, every 1 minute put 1 portion sugar, and every 2 minutes put 3 portion rabbit. Oh yeah, it's 2. Sorry. Every 3 minutes put 2 portion tomato and it's every 3 minutes put 4 portion of tomato. Every 4 minutes put 1 portion water. I give you this, you cannot get this soup ready.
Yeah, that one, yeah.
Yeah, but this is the same thing. I'm right. Like this means frequency, which means every 1 minute, every 2 minutes, every 3 minutes, every 4 minutes, you put one sugar. Every 2 minutes you put three bread beef. Every 3 minutes you put four tomato. Every 4 minutes seconds you put one beef minute. Yes. So it's the same thing. Am I right? So can you get the soup ready? If I give this to you.
After you explain it.
Oh, okay. Yeah. I will explain it to you. Yeah. Which means for the frequency and for the time, like if you use the frequency recipe and the time domain recipe, you can all get this soup ready. I'm right. Yeah, but why I want to why we want to talk about the frequency domain? Because the time domain, you can see it's very easy for you. I'm right. It's very direct, easy for you. But why I want to like use the frequency domain to represent signals or system or event or things? You know why?
Easier to look at.
Are you sure it's easier? It's still not easier to look at. Actually, you can see if you use the time domain recipe, I need to give you like until like 7 p.m. right? Because it's if the like soup needs 1 hour to make, right? So I need to give you 1 hour like a time domain like this figure. You can follow. Then you can prepare this soup. But for the frequency domain, what I need to give it to you is just I give you this and the start and the end time. I'm right. Then you can see if you use the frequency domain to represent signals, you need like a limited like a storage. I'm right. So which means if you store this event or signals in your computer or in some either file, I'm right. You just need like a little information to represent it. I'm right. Yeah, this is one reason, and the other reason is for the time domain. If you want to like represent, if you want to analyze it, deal with it, it's not very easy. For example, I give you this recipe, but you are the chef, you are the like cooker, and someone doesn't like tomato. You need to move the tomato, am right? So which means you just try to find along this time, am right? Along this time to remove tomato all from this time domain, like time domain figure, am right? So you need to remove many times, am right? During this 1 hour. That makes sense to you? But for this first domain, if I just like tell you someone doesn't like tomato, you just need to remove this thing, and just follow those three, the last three. Am right? Yeah. So which means the frequency for the frequency domain, like when you look at the signal or events or some things in the frequency domain, it's easy to you to analyze or to deal with. That makes sense to you? Yeah, that's the reason why we want to talk about frequency domain. Okay, I will give you a example. Yeah, for example, yeah, this is a set function. Yeah, this set function is just from 0, and the amplitude is 1, and the frequency is 5. This is the same function, right? Yeah, and you can see if you represent these signals in time domain, this is you need to draw this figure. That makes sense to you? Yeah, but if you represent these signals in frequency domain, you just need to you need to just draw this figure. Okay, let me tell you. For the frequency domain representation, the x-axis is always frequency. Do you know that? Like for the frequency domain, the x-axis is always frequency, which means this is 1 hertz, 2 hertz, like 3 hertz, like it's just a frequency, am I right? Yeah, so which means your like signal is just a 5, like frequency is 5 and amplitude is 1. Yeah, so you just use this one to represent it. You can see the difference between them. Am I right? But like you just said, if I just give you this one, actually you cannot represent the signals. You cannot represent signals very accurate. Do you know why? Because I didn't give you start. All right. So when we talk about the fruit domain, I need to give you the start times like that. All right. Give you some some things with your fruit domain representation. Yeah. Okay. This is a fruit domain. Oh, any question about the time domain and the fruit domain? Okay, let's continue. Okay, let's try to do a historical overview. Yeah, can we represent arbitrary periodic signals by a set of sinusoidal of different frequency and phase angles? Yeah, can we? Actually, I just talked about it at the beginning of this class. Can we? Yeah, like I said, yeah, this one, Joseph Fourier. Yeah, this one. If you don't like a frequency, like a Fourier series, don't like frequency domain, you need to hit this guy because this guy proposes the frequency thing and the Fourier series, Fourier transform. Yeah, but yeah, you can see after experiments after that, so this one found any any periodic signals can be represented by a set of sinusoidal signals of different frequency and phase angles. Yeah, so you can see, like this is we know that this square wave, am I right? Square wave is periodic. Yeah, this square wave is periodic. What's the period for this square wave? Do you know? For example, this is a star. Huh? 6. This is 6. Yeah, 6.1. Let's do 6.2. It is period. Am I right? Yeah. Can you think this square will be presented by a set of sinusoidal signals? Yeah, like this is a square wave, am I right? Yeah, we know that this square wave is a periodic signal, am I right? Yeah. So can this square wave be presented by a set of sinusoidal signals? Yeah, it can. This one is just tell you how. You can see the green is one sign function, right? And the blue one is one sign function, and the yellow one is also is one sign function. And after you add them together, you can get a square wave function. Yeah. So yeah, actually we have any continuously periodic signal can be represented as a sum of sine waves or sinusoidal with different amplitudes, frequency, and phase shifts. Yeah, which means if I want to give you the frequency domain, I need to give you the a frequency and amplitude and the phase shift. Do you know what's a phase shift? We talk about. If I want to give you these signals, I give you this one is frequency, am I right? This is like amplitude, am I right? What is phase shift? Yeah, the phase shift actually it is where you can start, where these signals start. Yeah, that makes sense to you? Yeah, which means if I give you those three things, you can totally represent a sense in the frequency domain. That makes sense to you? Okay, let's continue to talk about. Yeah, this one is just what I want to show you. You can see. Let's try. Yeah, this is just an example. Okay, wait. Okay, where is my? Yeah, yeah, this is an example. Like Okay, I think this one doesn't have the. Yeah, this is just like how to like represent a square signal with using the sign, using. Eh, is this wrong? Okay. Then you can see this is when you have a one sense signal, and this is when you add different two, and this is when you add three different sense signal. And when your like sense function is like more enough, and you can get a sphere wave function. Yeah, this is just what we talk about, like an example. Yeah, and six. Okay. I need to make it. Yeah. Yeah. You can see if you want a perfect square wave, you need to make your frequency 16 hertz like that. Yeah. Okay, this is just an example. And let's continue. Okay, okay, let's check the other example. This one, you can see the white light. We all know like the white light, I'm right, the natural white light. Actually, after the white light goes through the optical prism, yeah, you can see the white light actually it is organized, it is formed by 7 different colors. I'm right? Do you know that this one? Yeah, actually, this white light is just similar like a one thing, one event, and this 7 different colors is just like a different frequency. The different frequency, form this specific thing. This like a soup, like making soup, and these 4 different frequency things, and just form one specific event, like make this soup. Yeah. Okay, let me ask you a question. For a specific thing, also for specific signals, it is a time domain, is a frequency domain like a form, like a representation. It's always same. Is it always same? Like for one specific thing or one specific signal, or like is if their frequency domain representation always same? Do you think? Yeah, let me ask you an example question. We know like when we speak, am I right? Our like sound is is always like a combination like by a group of different frequency. Am I right? So do you think like for a specific people, for example me, if I speak, my frequency sound is fixed or not? No. Uh, mm, maybe I'm not a very good example because sometimes I will like lower my voice, sometimes I will higher my voice. But let me ask you for a piano, for a specific piano, if for this piano, if their like frequency is fixed, it's like frequency domain signals is always fixed or it will change for a specific piano. Yeah. Yeah. It fixed. I'm right? Yeah, you are right. Actually, you can see why the piano and the like a channel. Yeah, I know like Greece plays a channel. I'm right, and like other guitar or flute. Do you know why those different instruments have different sound? Do you know? Do you why? Huh? Temper? Timbre?
Well, that's what it's called.
Yeah. TIABR. Yeah, maybe, but I want to say that maybe the fundamental thing is for different instruments, it has different frequency. Yeah. Yeah, let me show you the other example. It will help you to understand. This one. Wait. Let me try to use this. Sound. Okay, I hope you can hear this one.
So I'm going to play that low note again, okay? And then I'm going to blow a little bit harder and see if I can find.
Wait for a little bit. Let me try to adjust the mic. Okay. Wait. Okay, I hope you can hear. But
that low note again, okay? And then I'm going to blow a little bit harder and see if I can find those other frequencies that this.
okay.
So I'm going to play that low note again, okay? And then I'm going to blow a little bit harder and see if I can find those other frequencies that this tube likes, okay? So I'm not going to change my fingers. And if you've been watching up here, this is kind of fun to watch, right? You can just turn this on at a party or something and have a little fun. So what we're seeing here is it's kind of like a frequency finder. So this program is picking up what frequencies are being heard in the room. So if I play the flute one more time, just to see this lowest frequency that I'm actually playing, okay?
All those spikes are other tones that are being played at the same
At
time?
the same time. So your ear is great. It says, well, I know that the highest one.
We think we're only hearing the first one on the left.
That's right. It's exactly right. So your ear says, okay, I understand that this frequency that I'm playing is around 500 hertz. If you look at the bottom line here, and the highest one, the strongest one, the one that your ear understands is the note, is that first one. Okay. But what makes it sound like a flute, what gives it its tone color or timbre, as you may have heard before, is the fact that you have a lot of other things happening that you don't really perceive as being the note. But it also means that if you follow, as I play here in a moment, if you follow, I'm going to play the low note. As I blow harder, I can actually play on that second highest peak. Okay, and these are called harmonics. Try again. So as I blow harder and harder, I'm actually going up onto those different harmonics.
Did you understand? Yeah, which means for the piano, for the flute, are actually for different instrument.
Like for Trump, we did the same thing, E sharp and F sharp, you press the same button, there's a pushing button, like pressure.
Yeah, I think not only for the instruments. Yeah, I mean.
No, I would say, technically, for any instrument.
Yeah, you're right. Yeah, you can see. Actually, for the specific instrument or other things or some things, actually for the flute, it's just the sounds doesn't put by the specific frequency, am I right? The different too is just for this frequency, you just higher. For the other two, it's just this frequency it has, but it always combined with a specific frequency. And that makes sense to you? Yeah, this is just the frequency thing. Okay, and then let's talk about that. Let's before we continue, let's talk about like okay, why we want to learn the Fourier series? Okay, before we talk about why we learn Fourier series, let's talk about how do we present a 3D vector. How do we present a 3D vector? Do you know? Yeah. That's right. This one, I'm right. Huh? Yeah, this one, I'm right. Yeah, this is like if you have a 3D vector like this P, I'm right, and you try to like project it to the x-axis, y-axis, and z-axis, I'm right. Yeah, and then this is presented to x-axis, y-axis, z-axis, and then this is just a if you want to represent this 3D vector, you just give ABC like that. And this is just try to, and actually the Fourier series is a similar thing. Yeah, this P, you call this one, right? If you learn the 3D vector thing. Yeah, actually the Fourier series is similar thing. Yeah, for a specific signal, right? You will like have this signal. Actually, you only can see one signal, but it is like generated by a group of different frequency signal. I'm right. So for this frequency, you just need to find the specific frequency like atom, and then add them together like that. Yeah, the Fourier series. Do you know this is series? What does that mean? A grouping of thing, am I right? Yeah, the first series is just I just find a grouping of frequency thing, and this grouping of frequency is just represent this signal or this event or these things. That makes sense to you? Yeah, that's the reason why the Fourier series. Yeah, this is if we learn the 3D vector, this is analysis for the 3D vector. This is the synthesis. I'm right. Yeah, actually for the Fourier series, it's same thing. We have the analysis form. We also have a synthesis form. Okay, let's try to record two basic periodic signals. Do you know what are those? Actually, we learned this in chapter 1. Two different. Actually, we have already talked about it in the beginning of this class. Complex exponential signals, and the other is sinusoidal signals. Yeah, those are two basic periodic signals. Yeah, the periodic complex exponential signals are defined. Actually, this we have already talked about in chapter 1. Yeah, we use this form to represent complex exponential signals. And what's a period? What's a fundamental period? Do you remember that table? What's a fundamental period? Since this is complex exponential signal is periodic, what is a period for this thing? Fundamental period. What? Are you sure? That table, do you remember? Like a fundamental period table. Yeah, 2 pi over omega naught. So omega naught, we call it a fundamental like frequency, am I right? Yeah. Okay. And the periodic sinusoidal signals are defined like this. Yeah. And the period is just similar like this. Am I right? Yeah. And the relationship between two basic periodic signals is what? You know? That equation. How to transfer the complex exponential signal to the sinusoidal signal? Yeah, what's the name for that? Yeah, Euler equation. Yeah, just try to, Euler equation. We can, using Euler equation, we can connect those two together, am I right? Yeah, so this is just, we have already talked about in chapter 1. Yeah, and based on this one, you can see this one is just, we call it like a real part. Yeah, because you can see this is just a real part, and this is just a complex part. Yeah, like a imaginary part. Yeah, this is just an imaginary part. Am I right? Yeah, any questions so far? Okay, and then let's try to talk about the harmonic Fourier series terms for periodic signal representation. Okay. Given periodic signals, yeah, what's a periodic signal? Which means we can find a periodic, period, let the xt equal xt minus like a t. What's the period for this signal? Huh? Are you sure? It's an easy one. Are you sure? What's a period? What's a period? What period means after you add this like time, it will repeat, am I right? So for this one, what's a period? Yeah, it should be capital T, am I right? Yeah, after T, it will repeat, after T, it will repeat, am I right? Yeah, so then, yeah, but we know like the T is a fundamental period. So the fundamental frequency we can easily to get, am I right? Yeah, okay. And then this is just the harmonically related complex exponentials. Yeah, we just use these equations to like to represent the harmonic related complex exponentials, which means this one like as a different key, it will like have different frequency, different periodic, am I right? And then this is just a harmonic related sinusoidal signals. Yeah. Yeah, this is just a definition. Like what is a harmonically related complex exponentials? What is harmonically related sinusoidal signals? Do you know why we call it harmonically related? What is harmonical mean? What does harmonic mean? Do you know? Yeah. Yeah. Yeah.
Bit one. It's like the string, harmonic, chord,
yeah, 3/2, 4/2. Yeah, it has some rule, am I right? In the specific like time, it's yeah, harmonic is just like like in the specific duration like that, am I right? But did you notice that the key here is 0, 1, 2, 3, like from -3, it's just like a different key. It's just like different frequency, different period. I'm right. It's just similar like harmonical thing. I'm right. Like a 1, 2, 3, 4, 5. And if you involve the negative 3, -2, -1, -0, 1, 2, 3. I'm right. Yeah. So the harmonic related sinusoidal, you can see this key as a key change, and it's just like a similar like a harmonical 0, 1, 2, 3. I'm right. Yeah, that's the reason why we define this as harmonic related complex exponentials and harmonic related sinusoidal signal. Am I right? Okay. Okay, let's try to talk about this question. What is the relationship between their periods? Like we just talked about the specific for the harmonic related complex exponentials. What is the relationship between their periods based on different key? Let's talk about what is a period. Period. What's a like a period for this thing? You know? Like what's the fundamental period? 2 pi omega 2 pi divided omega now, am I right? This is like a fundamental period, am I right? But here there is a key, which means you just add a key here. This is just based on different key. It has different period, am I right? Yeah. So, which means the t key will equal t over k, am I right? That makes sense to you? Yeah, because the 2 pi divided omega now is t, am I right? Is a fundamental period. Yeah. So this is just the relationship between their periods. It's just like a multiple 1 over k. Am I right? Did you you just mentioned like for the music, it is a half, like a three, like a third and fourth, like that. It's similar, yeah, yeah, because the period is like a 1/2, 1/3, 1/4, like that, yeah. So the question, when we add those signals together, what will be the fundamental? When we add those signals together, what will be the fundamental period frequency? Yeah, because since the signals will be represented by a set of Fourier series, am I right? So we want to add them together and like form the total signal, am I, the whole signal, am I right? So we need to talk about this question. Sorry. This one. So when we add those signals together, what will be the fundamental period? Do you know?
You have like 2/1, 2/2, I mean 2/2.
Yeah, like that. Which means, are
0.
you sure it's 0? Yeah, you can say you need to like a t over 1, like a plus t over 2 plus t over 3 plus t over 4, blah 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 blah. That plus like a t over, yeah.
But what if they be like t over -2,
Yeah.
3? So when you add them, what we do?
Oh, sorry. You cannot write it like this. It's just like because this is just not the e, like not the like it's just not the like the t plus together. Hey, you're right. Like t plus t 1. Let's just ignore 0, am I right? And t plus 2 plus 3, blah blah blah. Insist that t over -2, blah blah blah. It will remove, am I right?
Yeah.
Yeah. So then we just left 0, am I right? But you can see k cannot be 0.
Yeah.
Yeah, for this equation, am I right? So for the k, if k is 0, we just left one atom, am I right? So which means the period is just that atom. That makes sense to you? Yeah, it's t. Yeah, a fundamental will be omega now. Am I right? Yeah. So which means for this, you just add for the it's just for the specific like one. Yeah, that makes sense to you? Yeah. Okay. Then, yeah, the Fourier series term in pink gets superposition result in sawtooth wave. Like you just add those all those together and just get the final result like that, final signals. Am I right? So that's how. Okay, I will now talk about more new things. Okay, what is Fourier series?
The series together.
Yeah, the series, you can see actually you can see the E, this is just a periodic signal, am I right? The Fourier series is just you just use these periodic signals, but a set of periodic signal. The key is different, am I right? Yeah, you just add them together to represent a signal. Am I right? Yeah, that's right. You got that. Yeah, this is Fourier series. Yeah, we just use a set of this uncomplex exponential function to represent signals. Yeah, this is just like a kind of a harmonically series thing. So we call it a Fourier series. Yeah, we will continue to talk about more about Fourier series next class. Okay, any questions? Honey, do you want to make up exam 2?
Five's about,
Okay.
I don't